Chemistry, the Central Science, Chapter 9, Molecular Geometry and Bonding Theories, Lesson 2. So in the first lesson, we looked at VSEPR, which was valence shell electron pair repulsion. So that's a bonding theory that allows us to predict shapes. And it does a really good job of doing that, of predicting the shapes based on bonded pairs versus non-bonded pairs of electrons. So how can we use a different type of theory to explain other types of bonds that we see? So the difference between diatomic hydrogen and diatomic fluorine. So bond enthalpy for hydrogen, 436.4 kilojoules per mole. Bond length is 74 picometers. Bond enthalpy for fluorine is 150.6 kilojoules per mole, but the bond length is 142 picometers. So why would these two things be different? If they both have single bonds, right? Lewis theories, if you draw these out, they each have single bonds. So should they not be the same? Well, it depends on what types of overlap we see in their orbitals. Hydrogen only has a 1s orbital. That's where its valence electrons are, or valence electron. So they overlap to share. If we're going to form a bond, our electrons have to be in the same space. In fluorine, however, our valence electrons sit in the p orbital, the 2p orbital. So now we're going to have an overlap of our p orbitals. And remember, they're different in shape, right? S is a sphere, and the p orbitals look like an infinity symbol, or we call those dumbbells. So your valence bond theory then basically states that bonds are formed by sharing electrons from overlapping atomic orbitals. So let's take a look at ammonia. Nitrogen's electron configuration. So we have 2 electrons in the 1s, 2 electrons in the 2s, and 3 electrons in the 2p. So the 1s electrons are not participating in anything. Those are core electrons. Our valence electrons are in our outermost shell, our second shell. Hydrogen brings 1 electron in its 1s orbital, so it can help to fill the octet for nitrogen by joining the p orbitals. So if we're going to have ammonia, we're going to see an overlap between the 1s orbital on each hydrogen and the 2p orbital on nitrogen. However, when we look at this, what would the geometry be? Because we know that VSEPR predicts NH3 to be trigonal pyramidal, because we have 1 lone pair of electrons, 3 bonded pairs, which your electron domain geometry is tetrahedral, but because we do have that lone pair, your actual shape is trigonal pyramidal. When we look at our p orbitals, we know that they go along the axes, right? Px, py, pz. This would predict then that our orbitals, or that our bond angle, would be 90 degrees. However, it's not. It's 107.3 degrees. So then how can we explain this, right? So part of valence bond theory is looking at hybridization. So you take 2 orbitals. Non-equivalent means S and P, or S and P and D. So they're different. You mix them together to form a different shape, which allows you to do better overlapping with your neighbor atoms so that you can share electrons more effectively. When you make your hybrid orbitals, it's equal to the number of pure atomic orbitals used in the hybridization process. So when you form your covalent bonds, you're either overlapping hybrid orbitals with atomic orbitals with atomic orbitals, or hybrid orbitals with other hybrid orbitals. So how can we predict our hybridization? You draw the Lewis structure of the molecule. You count all of your pairs of electrons. So you're looking at your electron domain geometry. However many orbitals you have, or whatever your electron domain geometry is, that's the number of orbitals that you have to have. So if you have 2, that means you need 2 orbitals, and we always start with our lowest energy orbitals first. So you hybridize an s and a p orbital, 2 orbitals, sp, you get 2 sp orbitals out of it. Your example is a linear molecule, BeCl2. For 3 electron domains, you need 3 atomic orbitals to mix together. So you take an s and 2 of your p's, sp2, you get 3 new orbitals. because you mixed 3 atomic orbitals together, so you can hold 3 things around the central atom, whether this be bonds or lone pairs. Boron trifluoride. For 4-electron domain, you have to mix 4 atomic orbitals to get 4 new hybrid orbitals, sp3, right? S plus 3 p's gives you 4. So this would be anything with a tetrahedral electron domain, methane, ammonia, or water. If you have 5 in your electron domain, you need 5 orbitals. We've used our S, we've used our 3p's, so now we're going to bring a D into the mix. So we have sp3d. Because you mixed 5 atomic orbitals, you get 5 hybrid orbitals out of it, so you can accommodate 5 things around the central atom, whether those are bonds or lone pairs. So this is really just a counting game. Once you've identified your shape, it matches up to your hybrid orbitals. So the last one here, your electron domain of 6, means you need 6 atomic orbitals. When you hybridize those, then you get sp3d squared. So S plus 3p plus 2d gives you 6. So 6 new hybrid orbitals to accommodate 6 things around your central atom, whether those are lone pairs or bonded pairs. And we can't go any higher than 6 because electrons repel each other. There's no space there to occupy anything else. So with this, in terms of hybridization, once you have identified your shape, you've already counted out your number of bonds and your number of lone pairs. So you have your electron domain, and it just matches. So once you do your counting, you're just matching it. So the next slides are going to look at how do we form sp3, sp2, and sp hybrid orbitals. So you take one of your s orbitals, you take one of your p for sp3, your s orbital, you mix it together with your 3p orbitals, you get 4 new orbitals out of it that face along the vertices of a pyramid, right? And so this is how then when you mix these things together, when you have 4 total things around your central atom, you end up with a tetrahedral domain. So the hybrid orbitals are just forming a new orbital that's going to allow for better overlap. So at the 4 corners of that pyramid allows us to bond better and allows us to explain, the hybridization explains why do we see a geometry of 109.5 for methane. Why do we see a bond angle of 107.3 for ammonia and water, etc.? So you hybridize your orbitals, it then matches the bond angles that we see through X-ray crystallography. So the formation of sp2 hybrid orbitals, you take an S, you mix it with 2 p orbitals, you get 3 new orbitals, and you have 1 unhybridized orbital. So just because we didn't use it doesn't mean it goes away. So now our hybrid orbitals are at the vertices of a triangle, which allows for trigonal planar in shape and predicts the correct bond angle of 120 degrees, as in boron trifluoride. So what about formation of an sp hybrid orbital? You take an S, you take a p, you mix them together, you get 2 new orbitals, which we call sp, and now that can show us how we end up with something that is linear in shape with a bond angle of 180 degrees. So some specific hybridization on carbon to show then how we can get multiple bonds. So carbon atom, right, ground state, we ignore the inner electrons, the core electrons. Carbon has 4 valence electrons, 2s2, 2p2. Well, if we promote an electron to one of the p orbitals, so now we have 4 electrons in 4 different orbitals, and we just hybridize the s with 2 of the p's. We still have an electron then existing in one of the p orbitals. So that's what this is showing here. So then what happens? Well, we know that when we have an sp2 hybridization, we end up with a trigonal planar structure, which is what the green balloons are showing. The unhybridized orbital is shown there in gray. So we can accommodate these atoms around or accommodate bonds around the green. So the bonding in ethylene, which is sp2 hybridization, shows then how each carbon is sp2 hybridized, which sits in the plane of a paper, right? So those are your green. Now, if we flip it so that we're looking at it from the side, right? The dashed line and the wedge line here are showing that we're connected to the hydrogen atoms. So the unhybridized orbitals, each carbon has one electron in that. So now we're able to overlap those orbitals to form our double bond. So we talk about sigma bonds versus pi bonds, and a sigma bond is going to involve axial overlap. So when you are overlapping your hybrid orbital with another hybrid orbital or a hybrid to an atomic orbital. Your pi bonds are going to be multiple bonds, forming a double bond or forming a triple bond. Those result from overlapping your unhybridized orbital. So in ethylene, your pi bond is because your 2pz orbitals are able to overlap and share those electrons. The reason why this happens is when we're going to form multiple bonds, we cannot just have all of the electrons concentrated in just this singular area. Although we know they have to be located between the two atoms, if they're too close to each other, they're going to repel and it's not stable. So in looking at an electron density map for ethylene, right, our C2H4, we can see that yes, indeed, where the hydrogens are cool, right? No, the hydrogens aren't pulling electrons towards it, but we see the hot regions where there is electron density is above and below the plane of the molecule, which is resulting from the pi bond, where we're overlapping our unhybridized p orbitals. So how can we apply the same concept for when we hybridize carbon with an sp, with two sp hybrids? And whether it's on carbon or something else, sp2, sp, the hybridization is going to occur in the same way. So once again, we excite our electrons so that we have individual electrons in each of our atomic orbitals. Now we just hybridized an s with a p so that we end up with two new sp orbitals, and then we have two unhybridized orbitals. So this allows for the linear shape that we see. So we're overlapping our carbon to carbon, and then we're overlapping carbon to hydrogen to form our single bonds, which is also called sigma. So then what happens? Well, we have our pz orbitals unhybridized, as well as our py orbitals unhybridized. So then this allows for this hot dog looking thing, right? Which is showing your two pi bonds that form in acetylene, because acetylene is going to have a triple bonded carbons in it. So our sigmas go along the axis of our sp orbitals, and then it's basically like we're going above and below and then wrapping around to the sides so that we can accommodate these electrons then in our pi bonds. Looking at the electron density, we of course see it's nice and hot there between the two carbon atoms because that is where the electron density is, both above and below, around to the outside, and of course in the middle. So that's where all of our electrons are focused. So how can we describe the bonding in carbon dioxide? Well, that's formaldehyde. On carbon, right, we have three things surrounding it. If we have three things, we know we need three orbitals. So what is our hybridization? Because we have something trigonal planar, then we know the carbon has to be sp2. Oxygen also has to be sp2. So if two atoms are going to bond, they need to have the same hybridization if you're forming multiple bonds. So here we're showing along the axial regions are where the green balloons are, right? And then our pi bond occurs from our unhybridized p orbital on carbon and one of our unhybridized orbitals on oxygen. And then we have our lone pairs accommodated on oxygen in part of our sp2 orbitals. So that's not carbon dioxide, that's formaldehyde. So just a review in terms of how do we count our bonds. A single bond is a sigma bond. A double bond is 1 sigma and 1 pi bond, and then a triple bond is going to be 1 sigma bond and 2 pi bonds. So everything has to start off with a single bond. Without a single bond, you can't have multiple bonds. And then you add on pi bonds to get to your double bonds and your triple bonds. So this is true no matter what's bonded. If you have a double bond, 1 sigma, 1 pi. If you have a triple bond, 1 sigma and 2 pi. So if we look at acetic acid, how many single sigma bonds and how many pi bonds do we have? Well, you're just counting, right? So carbon to hydrogen, that's 3. The carbon to carbon is 4. Carbon to the single oxygen is 5. Oxygen to hydrogen is 6. And then carbon double bonded oxygen is another sigma bond there. So that gives us a total of 7 sigma bonds. And then our double bond has the pi bond as well. So we have 7 sigma and 1 pi. So let's talk for just a moment about delocalized molecular orbitals in terms of what can explain certain types of resonance that we might see in a structure. So our example here is benzene, C6H6. This is an aromatic compound. So each carbon, by looking at it, we count our green balloons around it. We know that it's sp2 hybridized. Everything is sitting there flat in a plane. Everything is trigonal planar to each other. 120 degrees separates it. If you draw out this structure, you would see alternating single bonds and double bonds. So a delocalized pi orbital then is allowing us to see, hey, all of these unhybridized p orbitals line up above and below the plane of the molecule. So effectively, they can all overlap, and then it almost looks like 2 donuts, right, sitting on top of and below the ring, which then allows for sharing of those pi electrons across the entire molecule. So if you draw out benzene, it would be alternating single bond, double bond. You could move those to show the resonance, but of course we know with resonance, it doesn't necessarily mean that one of those truly exists. And in benzene, what makes it so stable is the fact that you have this delocalization such that your electrons are shared throughout all of these unhybridized orbitals. So not all molecules can have delocalization in terms of their electrons, right? Delocalization means they're kind of everywhere. A localized, right, electrons means that they sit between these 2 atoms and they don't move.